it's running in real mode. The first thing it does is giving the control to the BIOS. The BIOS performs several operations, like finding your hardware. Okay, if you have, for instance, a RAM or a hard drive, it is responsible for finding them. This is the first operation. And then it creates a very special zone inside the RAM, which is called the interrupt vector table. So each vector contains the address of a routine, which will be called when calling a particular interrupt. Then the BIOS triggers an interruption 19, which is responsible for loading the master boot record from the drive or device to be used as a booting medium into the RAM and jumping to its entry point, which is fixed. Thank you, Izzy. This bootloader is responsible for loading the kernel. Okay? And the tasks done by the kernel are typically first switch to protected mode, okay, and copy the interrupt vector table to a special zone. So the address is going to depend on your kernel split, but typically it's in the first page. So from this diagram, what we understand is that everything, once the kernel is booted, runs in protected mode. Okay? So this is kind of a problem if you want to use virtual mode, right? I mean, everything is running in protected mode. It means even if when you boot a particular virtual machine inside of if you try to run a particular OS inside as a guest, inside an hypervisor, when you boot it, so it simulates real mode, so the OS can boot, but it's actually all running in protected mode. So it looks like game over. What we could try to do is somehow, from a protected mode task, try to get back to either real mode or virtual mode. So we can restart doing addressing, disable segmentation, disable paging, and restart having fun with interrupts. Theoretically, this is possible. Well, this is totally stolen from Frac. So if you guys read Frac once in a while, this was from the paper of the Demon, and he was supposed to give us a favor of do us a talk, but for some reason, okay, it was his girlfriend's birthday or some bullshit like that. So he didn't make it. He didn't make it. And thank you very much to Casper for replacing his talk. So what happens is that when we're in protected mode, we could very much either switch to real mode or switch to virtual mode just by setting a few registers, CR registers, which are control registers. Okay, obviously this requires ring 0 privileges, but still, it could be possible. As opposed to switching to SMM, which is not directly possible in most cases. Okay, you need an SME interrupt or something like that, and it's typically disabled in most BIOSes nowadays. Okay, this is taken from the Linux kernel, and this is a switch to real mode, from protected mode to real mode. So what we see is that by manipulating the control registers 0 and 3, it is typically possible to get back to protected mode, to real mode, sorry. So would we like to do that? Actually, this won't work inside a virtual machine, because the control registers obviously are very much part of the emulation of the virtual machine. So if we try to do that, we're going to have a simulated switch to virtual mode, but we're still going to be trapped inside a task running in protected mode. So we'll still have paging and stuff, and we won't be able to call the interrupts the way we want to. But good news is, most operating systems offer a way to access a sort of virtual mode directory, so that users can run 16-bit applications. So for instance, under Windows, you have what's called NTVDM. Okay, maybe this is not too familiar to you, but this must be common com, right? You can run old school MS-DOS 16-bit applications inside Windows. So this is completely emulated. It's not a read switch to virtual 8086 mode, but still you can use it. Under Linux, things were done basically to run DOS and U, so very much for the same reason, be able to emulate a 16-bit environment to run MS-DOS applications. So for some reason, we have two syscalls available. It was first introduced in kernel 09 something, and the first one was called VM86. And since the API was so great, it has been renamed as VM86 Fold, and a new one has been introduced as VM86. If we look at this API, they take as an argument a complex structure, which is a kernel structure, to pass argument to the kernel. So if we look at those two syscalls are using a different structure, but good news is inside those structure there is a pointer to another structure, which is the same in both cases. So if we take a look at it, the argument